Look at every fighter jet that has ever entered operational service, from the P-51 Mustang of World War II to the F-22 Raptor flying today, and you will see the same fundamental design feature: a vertical tail, sometimes two of them. The vertical tail is so universal in aircraft design that most people never think to question it. It is simply part of what an airplane looks like. But right now, the most advanced combat aircraft being developed and tested around the world, China's J-36, America's sixth-generation concepts, and a range of classified demonstrators are eliminating the vertical tail entirely. This is not an aesthetic choice. It is a physics-driven engineering revolution that changes everything about how a combat aircraft performs, survives, and fights. And understanding why it is happening requires going back to the fundamentals of how aircraft actually fly. Leave your like, subscribe, and share. Let's begin. The vertical tail exists to solve a specific aerodynamic problem called yaw stability and control. When an aircraft flies through the air, it is subject to forces in all three axes of motion: pitch, which is the nose-up and nose-down rotation; roll, which is the rotation around the aircraft's long axis; and yaw, which is the rotation of the nose left and right. Pitch is controlled by the horizontal tail or canard surfaces. Roll is controlled primarily by the ailerons on the wings. Yaw is controlled by the rudder, which is the movable surface on the vertical tail. Without a vertical tail, an aircraft in conventional flight would be directionally unstable. It would weather vane into crosswinds, skid sideways in turns, and be extremely difficult to control. The vertical tail is essentially a large fin that keeps the aircraft pointing in the direction it is traveling and allows the pilot to precisely control heading. The problem with the vertical tail, from the perspective of modern combat aircraft design, is that it is one of the largest contributors to radar cross-section. Radar works by emitting radio frequency energy and detecting the reflections that bounce back from objects in the environment. The amount of energy that bounces back, the radar cross-section, is determined by the size, shape, and material properties of the reflecting surface. Flat surfaces that are perpendicular to the radar beam are the strongest reflectors. A vertical tail, which presents a large flat surface at close to perpendicular angles to radars approaching from the front or sides, is essentially a corner reflector, one of the worst possible shapes from a stealth perspective. The F-22, despite being the most capable stealth fighter in operational service, has two canted vertical tails that are angled inward to reduce their radar return compared to truly vertical surfaces. But they remain a significant contributor to the aircraft's overall signature. The radar cross-section numbers involved are not trivial. The F-22's radar cross-section is estimated at approximately 0.0001 square meters, roughly the size of a steel marble, which is an extraordinary achievement for an aircraft of its size and performance. But analyses of its signature consistently identify the vertical tails as one of the remaining areas where the signature is largest. The B-2A Spirit bomber solved this problem by using a pure flying wing design with no vertical tail at all, relying instead on split drag rudders at the wingtips for yaw control. The B-2 achieved a radar cross-section estimated at 0.0001 square meters or less, despite having a wingspan of 172 feet, a testament to how much radar energy the elimination of vertical tails can save. For a fighter aircraft, the challenge is replicating that stealth benefit while maintaining the agility and maneuverability that combat requires. The solution that modern designers are pursuing involves replacing the yaw control function of the vertical tail with a combination of other methods. The most important of these is thrust vectoring, the ability to deflect the exhaust from the aircraft's engines to generate direct forces and moments in any direction. The F-22 already uses two-dimensional thrust vectoring in the pitch axis, which is part of what gives it its extraordinary nose-pointing ability at low speeds. A tailless aircraft needs three-dimensional thrust vectoring, the ability to deflect thrust in both pitch and yaw, to replace the directional control that the vertical tail provides. Three-dimensional thrust vectoring systems have been tested extensively in research programs, and the F-119 engine's successor technologies are designed to provide this capability. The second yaw control method is differential control surface deflection. On a tailless aircraft with a swept wing, the control surfaces on the left and right wings can be deflected in opposite directions to generate a yawing moment, the left surfaces creating more drag than the right, for example, which pushes the nose to the left. This is similar to how the B-2A generates yaw control with its split drag rudders, but on a more capable and responsive scale. The challenge is that differential drag-based yaw control is less effective at high speeds and in aggressive maneuvering than a conventional rudder, which is why the fly-by-wire control system managing these surfaces must be extraordinarily fast and sophisticated. The fly-by-wire control law architecture is actually the enabling technology for tailless fighter design. A conventionally stable aircraft, one designed with inherent aerodynamic stability, can be flown manually because the aircraft naturally wants to return to level flight after a disturbance. A tailless fighter designed for maximum performance will be highly unstable. It will diverge from any given flight condition rapidly if the control surfaces are not continuously adjusted by the flight control computer. The F-16 was the first operational fighter designed with deliberate relaxed static stability, requiring a fly-by-wire system to be flyable. A tailless 6th-generation fighter takes this concept several steps further, requiring control law algorithms of extraordinary complexity running on processors fast enough to issue control surface commands hundreds of times per second. Leave your like, subscribe, and share. The aerodynamic benefits of eliminating the vertical tail extend beyond just radar cross-section reduction. The vertical tail generates drag. It is a surface area that the aircraft must push through the air at significant energy cost. Eliminating it reduces the aircraft's aerodynamic drag, which directly translates into higher top speed, greater range, or reduced fuel consumption depending on how the designer chooses to apply the benefit. For a 6th-generation fighter with the range requirements being demanded by the Pacific Theater, where combat radii of 1,000 miles or more are needed, every reduction in drag is valuable. The cranked kite or flying wing planforms being used in tailless designs also typically have better lift-to-drag ratios than conventional fighter configurations, further improving range and endurance. The weight savings from eliminating the vertical tail are also significant. The vertical tail of a large fighter aircraft, like the F-22, weighs hundreds of pounds. The structure itself, the actuators that move the rudder, the hydraulic or electromechanical systems that power those actuators, and the flight control computers and wiring that connect them. Eliminating all of this reduces the aircraft's empty weight, which either directly reduces the weight the engines must push through the air, or allows that weight margin to be used for additional fuel, weapons, or sensors. In the mass budget calculations that drive aircraft design, hundreds of pounds of savings are significant. The infrared signature benefits of tailless designs are less obvious, but equally important. Modern air defense systems do not rely solely on radar. They increasingly use infrared search and track systems, known as IRST, that detect the heat signatures of aircraft engines and aerodynamic heating. The exhaust plumes from fighter engines are powerful infrared sources that can be detected at ranges of tens of miles under favorable conditions. A tailless design allows aircraft designers more freedom in how they shape and shield the engine exhaust. The absence of a vertical tail means that the aft fuselage can be designed with different geometries that better conceal the exhaust from certain threat directions. Combined with engine designs that reduce exhaust temperature and mix hot exhaust with cooler air before it exits the aircraft, this can substantially reduce the infrared signature. The structural engineering challenges of tailless design are formidable. The vertical tail on a conventional aircraft does more than provide aerodynamic stability, it also carries structural loads. On a twin-engine aircraft, the vertical tails are structural members that tie together the aft fuselage and help carry the loads generated by the engines and horizontal tails. Removing them requires redistributing those structural loads through the airframe in ways that add complexity to the structural design. The cranked kite wing used in designs like the J-36 and the concepts that influenced NGAD addresses this by using a thick, structurally efficient wing root that can carry the loads previously shared between the fuselage and vertical tails. Advanced composite materials, carbon fiber reinforced polymers, ceramic matrix composites in high-temperature areas, make this structural rearrangement feasible at acceptable weight. The weapons integration challenge for tailless fighters deserves attention. A conventional fighter with vertical tails has a natural location to mount sensors, antennas, and sometimes weapons, the tail surfaces and the aft fuselage between them. A tailless design must accommodate all of these elements within the wing and fuselage structure. which drives specific requirements for internal volume and access. The large internal weapons bays that tailless designs tend to have, because the thick wing root provides natural volume for weapons carriage, actually help here. But the antenna farm and sensor placement challenges require careful design work. The radio frequency apertures for radar, electronic warfare, and communication systems must be embedded in the airframe surface in ways that do not compromise either the stealth signature or the structural integrity. The historical precedents for tailless aircraft in combat are limited but instructive. The Horten H-9, also designated HO-229, was a German World War II flying wing fighter bomber that represented the most advanced tailless combat aircraft concept of its era. Wind tunnel testing conducted by the Northrop Grumman Company in 2008 on a replica of the HO-229's nose section confirmed that the aircraft had radar-absorbing properties in its construction. Specifically, a mixture of charcoal, sawdust, and glue in the nose section that may have been a deliberate, if primitive, stealth measure. The HO-229 never flew in its fully developed fighter form, but the concept it represented, a flying wing combat aircraft with reduced radar signature, proved remarkably prescient. The B-2, which is the most successful tailless combat aircraft in history, validates the concept at operational scale. The F-117, despite its faceted appearance, actually retained a small V-tail, two canted surfaces at the rear that provided some directional stability. Even this heavily compromised concession to conventional design was accepted as a practical necessity given the control law limitations of the era. The subsequent generation of stealth aircraft, the B-2 and later concepts, eliminated even this compromise. The sixth-generation fighters now being developed represent the culmination of 40 years of learning about how to make tailless designs work in the demanding flight envelope of a combat aircraft. The Chinese J-36's tailless design carries a specific strategic message. China observed the same physics, conducted the same analysis, and reached the same conclusion as American designers. Eliminating the vertical tail is essential to achieving the radar cross-section needed to survive in the threat environment of the 2030s and beyond. The fact that two of the world's most advanced aviation programs independently converged on tailless design as the path forward for sixth-generation fighters is not a coincidence. It is physics asserting itself. The laws of electromagnetism and aerodynamics do not care about national boundaries. They simply define what is possible, and what is possible in a low observable high-performance combat aircraft in 2026 is a tailless flying wing that would have been uncontrollable without digital fly-by-wire, unbillable without advanced composites, and unimaginable without decades of classified research. The tails are coming off. The physics demanded it, the technology finally made it possible, and the threat environment made it necessary. What replaces the tail is not empty air. It is a combination of vectored thrust, intelligent control laws, and structural elegance that represents the highest expression of what aerospace engineering can achieve. When the F-47 eventually flies in public for the first time, and when the world sees what Boeing and the Air Force have built, the absence of a vertical tail will be the most visible sign of how profoundly the physics of combat aviation have been reimagined. Leave your like, subscribe, and share. Until next time.